and we are here to present our latest work, HyperMatch, which aims to improve semi-supervised learning methods by relaxing contrastive constraints, as the title shows. First, we would like to give an overview of our work. In summary, we proposed an enhanced contrastive learning method named HyperMatch to handle the effective separation and exploitation of clean and noisy pseudolabels. To alleviate the confirmation bias in semi-supervised learning, we relax the assignment of noisy samples by categorizing them into a hyperclass instead of a single class. And the hyperclass here is a union of top k nearest classes. Then our proposed relaxed contrastive loss is only applied to those noisy samples. Our method achieves state-of-the-art performance on several SSL benchmarks. Semi-supervised learning, which is different from supervised learning and unsupervised learning methods, is a machine learning approach that combines both labeled data and unlabeled data to build very predictive models whose performance can exceed the performance obtained using only labeled data. The information inferred from the unlabeled cluster could help place the decision boundary. Current semi-supervised learning methods utilize pseudo-labeling as a basic technique. However, there is a long-existing problem. The model would make overconfident errors during training and reinforces those misclassified patterns, while ignoring or underweighting evidence that contradicts them. This problematic phenomenon is named confirmation bias, which prevents the model from further improving its performance. In the right figure, as we can see, the test accuracy of fixed match actually drops after a long period of training due to confirmation bias, and this inspires us to tackle the problem. Another related field is contrastive learning. Contrastive learning is a self-supervised learning technique that aims to learn useful representations from unlabeled data by maximizing the similarity between positive pairs while minimizing the similarity between negative pairs. It has gained significant attention and achieved remarkable success in various domains, including computer vision and natural language processing. It's very helpful to learn well-clustered representations. The confirmation bias comes from the incorrect class assignment, as figure A shows. Once the instance is assigned to a round cluster, it is pulled close to the round pseudolabel class and pushed away from the ground truth class, and this would be exaggerated during training. To alleviate this problem, we want the sample to be able to interact with its ground truth class to make it possible to rectify its predictions. To achieve this order, we relax the class assignment and assign the instance to a hyperclass instead of a single class. Here, the hyperclass is a union of its top k nearest classes, where the ground truth class is much more likely to lie in, as figure B shows. Also, we can indicate from the top k accuracy of pseudolabels that top k accuracy would be much better than top ones, and the noisy labels actually benefit much more than clean labels. This is our basic motivation. Our proposed HyperMatch composes of two components: pseudolabel partition and relaxed contrastive loss. Pseudolabel partition consists of two parts. The first one is class distribution calibration. The semantic similarities with respect to prototypes are integrated to calibrate class distributions, so that the final distributions would be more smooth and more unbiased. Then followed by GMM noise modeling. A two-component GMM model is applied to fit on the calibrated distributions and split the unlabeled data batch into clean batch and noisy batch. Finally, we inspired by contrastive loss and proposed a relaxed contrastive loss, which allows an instance to interact with the top k class of another instance. However, this would introduce much noise as most of the class connections are redundant and incorrect. To reduce the noise, we only apply the relaxed contrastive loss to the noisy sample split by the GMM, with standard contrastive loss applied on clean samples. In such a way, we relax the class assignment and reduce the probable noise for better learning. For a better understanding, here we compared with other contrastive losses. The self-supervised contrastive loss considers two views augmented from the same image as positive, and any two views from different images are negative. For class-aware contrastive loss, the class information is included, and samples from the same class are regarded as positive, while samples from different classes are negative. Here, the class information is related to top 1 class. On the other hand, our relaxed contrastive loss not only considers the top 1 class matching, but also allows for top k class to be included in similarity calculation. This helps the noisy samples to find their ground truth classes instead of being pulled from an incorrect cluster. Our experiments are mainly conducted on standard image classification datasets such as CIFAR and STL10. HyperMatch achieves state-of-the-art performance on several benchmarks with various labeled datasets. Also, to show our ability in dealing with incorrect pseudolabels, we also compared with other methods on a more complex semi-INET dataset with out-of-distribution samples. With introduced relaxed contrastive loss, we achieved remarkable performance improvement also on fixed match. We also visualized the test accuracy and the pseudolabel accuracy. It is observed that HyperMatch shows fast convergence and better pseudolabel accuracy even compared with other contrastive learning-based methods. The accuracy drop caused by confirmation bias is much lower and happens later during training. Also, from the mitigated imbalance distributions of pseudolabel class indicates HyperMatch's ability to alleviate confirmation bias. And finally, this is all of our presentation. Thanks for your time.